Good afternoon, class. Today we're going to pick up with systems of equations and matrices. We did half of the assignment the last time. A little over half, you might say.
Actually, 2/3.
And maybe we should remind them of determinants before we go on. I'm going to remind y'all of the last thing we were doing, okay? We're going to be, we were finding determinants. And we were looking at 2x2 and 3x3 matrices. Remember, a 2x2 matrix has 2 rows and 2 columns. So if we had, let's say, 7, 4, -3, and -8 there. This was the easier of the two types of determinants. We multiply. Remember, it's the difference of the cross products when you start in the upper left-hand corner. Multiply 7 times -8 is -56 minus, and then we multiply again. 4 times -3 is a -12. That minus comes from the formula that I stated. You multiply, minus, multiply, and that minus a negative, that becomes plus a positive. So -56 plus 12, that gives me a -44 for my determinant. Do y'all remember doing that? Now 3x3 determinants were a little bit messier. So a 3x3, that means there are 3 rows and 3 columns. So 3 rows and 3 columns. We had a trick for finding 3x3 determinants. What did we do first? Okay, we recopy those first 2 columns out beside the vertical bar. The -1, 5, 1, and the 0, 4, 3. And then, instead of just 2 diagonals, we had multiple diagonals here. We had parentheses minus parentheses. The first parentheses contains the diagonals falling from left to right. You always start in that upper left-hand corner for determinants. -1 times 4 times 0. Oh, that's easy enough. It's just a 0. 0 times 2 times 1. That's another 0. And 1 times 5 times 3, that's a positive 15. We have 3 diagonals falling from left to right. You're now positioned at that 3rd number on the top row. You now begin falling from right to left for the next 3 diagonals. 1 times 4 times 1 is 4. -1 times 2 times 3 gives me a -6. And the last diagonal, 0 times 5 times 0, gives me +0. Now that flashing's bothering me. Then, simplify inside the parentheses. The first set of parentheses is just a 15. Minus 4 minus 6 is a -2, plus 0 stays a -2. What have I got for my determinant? Okay, so 15 plus 2 gives me 17 for my final answer. Any questions there? We said we would start with Cramer's rule. At the beginning of class the last time, we solved systems of equations, linear systems of equations, using elimination and substitution. We now have a new method of solving linear systems. It's called Cramer's rule, and it uses this notion of determinants. So I'll say Cramer's rule uses determinants. Tim, I did it again. Mark it together. Determinants uses determinants to solve, get it ready, linear systems. Oh, wow, look at that. White out courtesy of Samantha. Okay? So, when you're solving a linear system of equations, you saw elimination and substitution the last time. This new method uses determinants, and the advantage, if your solutions are fractions, then this Cramer's method is much easier because you don't wind up, oh, I need to plug in negative 7/9 for x to find y. So it is a very nice, clean method. If you're a programmer, it is a very easy method to program. If you're trying to write a program to solve a linear system.
I gotta look practice.
And so at this point, to solve a linear system, we saw substitution the last time. That's probably my least favorite form, least favorite method for solving systems. The second one, elimination. And as we saw, it's really, we use elimination and substitution combined. We eliminate to find one variable, we substitute to find the other. Now the third method, Cramer's rule. Let's look at number 13. Let me write the problem down. It says solve using Cramer's rule. We have a negative 3x plus 3y is equal to 1 for the first equation, and 8x plus 2y is equal to, is that a 12? For the second equation. Let's make sure we haven't, okay. Make sure I haven't miscopied. That's right. It's funny, Cramer did so much significant math research using determinants and matrices, but this is the one little thing he's remembered for. It's in all college algebra books. I suppose he'd roll over in his grave. He didn't think what the Cramer's rule was that significant, he being Cramer, but here's what he did. The first thing he did was find the determinant of the coefficient matrix. The coefficient matrix, remember, that just summarizes the coefficients of x and y. He called this determinant D. So D was the determinant of the coefficient matrix, negative 3, 8, 3, 2. Remember, you have to make sure that the x's and y's, that like variables, are aligned. Then the first column summarizes the x coefficients. The second column summarizes the y coefficients, and this is a 2 by 2 determinant. This is one of those short ones. You multiply -6 minus multiply 3 times 8 is 24. -6 minus 24 gives us a -30. So the first thing Cramer did was find the determinant of the coefficient matrix. Next, he found the determinant of the matrix that you get when you replace the x column with this column of constants here. So you're replacing the x coefficients with 1 and 12. He denoted this matrix D sub x, this determinant I should say, that you're replacing the subscripted column. You're replacing the x column with 112. The y column stays as it is. This y column, you only replace one column. It's the column that's subscripted. That's the one you replace. And he found this determinant. Multiply 1 times 2 is 2 minus multiply 3 times 12 is 36. 2 minus 36 is a -34.
I didn't miscopy the problem, did I? I'm wondering the same thing.
Let's just make sure I didn't miscopy the problem, because these numbers are not the numbers I was expecting. No, that's right.
Actually, it's a very good.
It's a good first problem, but I just wasn't expecting this to happen. Okay. Now, how many variables? There's two. For every variable, he found a subscripted determinant. He found d sub x. There's still a y variable, so he found d sub y. D sub y, you have the y column replaced. The x column goes back to the original values, -3, 8. You don't have more than one column replaced with that column of constants. With d sub y, the y column becomes 112. The x column becomes goes back to being -3, 8. Take a moment and look at that. Any questions on what he was doing? Whatever the subscript is, that's the column you replace in D. We then multiply. -3 times 12 is -36. Minus multiply 1 times 8 is 8. So we have a -36 minus 8. Is that a -44? And here's what Cramer was able to prove that lets his name live on in immortality in math textbooks. He was able to prove that the value of x will always equal d sub x divided by d. The value of x, d sub x is -34, divided by the d value is a -30. Negative divided by negative is... so we're going to have a positive. We can cancel a 2 above and below. 34 divided by 2 is 17. 30 divided by 2 gives me 15. So, these lines are going to intersect where the x value is 17 over 15. 17/15. Now with elimination or substitution, you then got to take that 17/15 and plug it in for x to find y. But what's nice about Cramer's rule is there's none of that messy plugging in. The value of y is equal to d sub y divided by d. And we better make a note. You're using d each time. You're using d each time, so you better make sure that you get the correct value of d. If you mess up in this first step here, then your final answers are all wrong. But d sub y was negative 44. D, we said, was negative 30. Negative divided by negative gives me a positive. The only thing that divides evenly into 44 and 30, what can I cancel? Other than 1, what's the only number that divides evenly into 44 and 30? 2. So 44 divided by 2 is 22. 30 divided by 2 is 15. We didn't have to plug in that messy fraction. We were able to use determinants to find the point of intersection.
That's the same answer you would have gotten with elimination or substitution, but no fractions to work with.
Notice, this is all numeric calculations. At no time do I need to combine like terms. I need to get all the x's on one side. This is strictly numeric. That's why it's such a popular method for programmers to solve systems, because it's just strictly numeric. And that's what computers do best, numeric. Well, I guess before AI, it's what computers did best, numeric calculations.
A word of warning, you've got to type it as an ordered pair, so be sure you have those parentheses.
Get out of that denominator. Don't put the comma in the denominator.
What do you think? You think they'd count it wrong if I do?
I guess go ahead and see.
I'm going to see. They were trying to, or some programmer was trying to go through and fix it where if you put the comma down there, it would count it right. Let's see, did they? Okay.
Oh, they did. Okay. Still, it's bad form.
That comma
it's bad form.
Okay.
Well, but this, looking back at this, that number 13, it illustrates why Cramer's rule is so nice. If you had, say you'd used elimination and substitution, you got 17/15. You then would have had to plug in the 17/15 for x and solve for y. I have no problem working with fractions. I can do it as easily as integers. It's y'all that mess up when you start plugging in fractions, okay? Some of y'all mess up, okay? Not all of you, but some of you do.
I think writing a program for them plugging in those things would be a little bit more difficult than just d, dx, dy.
That's right.
Okay, now number 14.
Okay, I guess I have enough paper here.
Oh, yeah. You can use a different page for every problem.
Okay, another Cramer's rule problem. 9x plus 4y equals 16. Keep in mind, we're just looking for points of intersection.
He's once again writing the constants in red.
8x plus 8y equals 72. Nine x plus 4y equals 16, and 8x plus 8y equals 72. And once again, they're telling us to use Cramer's rule. So we'll find, notice by the way that the x variables are aligned, the y variables are aligned, the constants have to be on the right hand side, and that's what we have. So the coefficients for x are 9, 8. The coefficients for y are 4, 8. we multiply 72 minus, and remember that minus comes from the definition of 2 by 2 determinant. Multiply 4 times 8 is 32. 72 minus 32 gives me a D value of 40. And you always start multiplying in the upper left-hand corner. If you had started here, 32 minus 72, you would have gotten a negative 40. You'll be off. If you don't start at the correct spot, then your determinant will be off by a sign every time. We have an x and a y, so we'll find d sub x. Dig out the calculator. The x column is 16 and 72. The y column stays the original values of 4, 8. So we multiply 16 times 8. Is that a 104? No, 108?
128.
120.
Oh, calculate.
Give it to me. Where is it? Okay. How do I do it?
I don't know. You're going to have to.
Samantha, you're going to have to teach me how to do it. How to use this fancy thing. I've never had anything. Look at what Samantha gave me.
Oh, Tim.
I don't know how to use it. She's going to have to teach me. Okay. Now, how do I know which side has the whiteout paper?
Oh.
Not with my vision. Not in this dim light. But I want to do that.
I think this is it.
Okay, do you press the button?
You know what? You just press down and drag. Try it like that, Tim.
Okay, here I go.
Try it like that. Did it do? Oh, you're doing it, Tim. But you're not supposed to just do it over and over. Then,
Oh, it does?
Well.
Oh, I'm going to have to practice with this, okay? So, I'm going to have to practice with it.
Oh, my gosh.
I'm so embarrassed. I'm not uploading this video. I'm not going to upload this video, okay? Oh, no, look at the old people not knowing how to use whiteout. Oh, wow. Now, I forgot what I'm doing. There's another whole person.
16 times 8 is 80 and 48.
128.
Look at my calculator.
Minus, I don't need your calculator. Wait a minute. 72 times 4, is that a 288?
Yeah.
128 minus 288, that's a negative 160.
Can y'all do the math in your head? Are we going to wind up with a fraction for x?
No, but still, I prefer. Cramer's rule is absolutely one of my favorite methods of solving linear systems. Now, oh wait, no, it's a d sub y. I did it again. A d sub y. What's the first column I'm going to write there? What numbers am I writing for d sub y?
Right for d sub y, that's dx.
I found dx. Now I'm finding dy. Okay, you see it goes back to the original numbers. You're only replacing one column at a time. I'll see people doing 1672, and then they'll replace the y column with 1672. If you have two of the exact same columns or rows, your determinant's going to turn out to be 0. So you only replace one column at a time. The 4, 8 is being replaced with the 1672. So 9 times 7, we multiply. 9 times 72, I'm going to cheat and look at Tony's calculator. 648. No, that isn't cheating. Looking at a calculator is not cheating. And then 16 times 8, that is a 128. Oops, wrong color. 648 minus 128 is going to give us a 520. I'll just write it right there. And Cramer, his thing that made him famous, he was able to prove that x will always equal d sub x divided by d all over 40. Negative 160 divided by 40 gives me a negative 4. So that means these two lines will intersect when x is equal to negative 4. The y value will always equal d sub y. Where's d sub y?
520.
That's the 520 divided by d, 40. And it's, what is that, 13? To give us y is equal to 13. So these lines intersect at the point negative 4, comma 13. Now, if it were a 3 by 3 system, then it'd be a little messier. The process, because the determinants would be longer, but the process still works. You find d sub x, d sub y. If it's a 3 by 3, there's another determinant you'd have to find. What is it?
You got an x, y, and a
Z, then you'd have to find d sub x, d sub y, and d sub z. But the process still works, okay? Any questions there?
in the semester and the course.
Now let's look at some applications of linear systems.
So 15 through 18 are word problems. We'll do 15 last. So you want to do?
Yeah.
Okay, we're going to move on to number 16. I don't think we're going to need a calculator.
Oh, I don't think so.
I'm going to close it. There.
A woman bought some large frames for $17 each and some small frames for $5 each at a closeout sale. If she bought 15 frames for $135, how many of each type? Find how many of each type she bought. Now, what do y'all think she means frames? I'm assuming picture frames, not glass frames. So, but maybe she has a gallery and she needs frames for the pictures she's displaying, what have you. But she's buying two different things, large frames and small frames. So those are the, maybe I should ask the class, what are the unknowns? What do we not know? What are we trying to, what did you do?
I didn't do anything. I didn't touch it.
Likely.
I hadn't touched it. Huh? Oh, okay. Well, just... It's still
okay.
recording.
It's still recording? Okay. I'm going to summarize the information they give us on a table, and that's my advice to you. When you run into a situation, a scenario like this where you're trying to find multiple quantities, try to summarize the information using a table. This is number 16. What are the unknown? What are the two things we don't know? How many of each type of frames that she bought? Switch to my paper. I'm going to write a little table here. I'll have large frames and small frames. And we've already said the thing we don't know is how many frames she bought. How many of each type? So I'll say number purchased. Or I could just out of laziness say quantity. Number purchased. Well, we don't know how many large frames she bought. We don't know how many small frames she bought. So I'll just say X and Y. Notice we need to switch back. I need to reread the problem. I'm taking the pieces apart, the pieces of information they've given us, and figuring out where to put it on this table. They tell us the selling price. The large frames cost $17 each. The small frames cost $5 each. Switch back. I'm going to put in a little column for selling price. The large frames cost $17 each. The small frames cost $5 each. I guess that's a good price. I haven't bought picture frames in a long time. That 17 seems sort of steep to me, but then again, I'm cheap, I suppose. But maybe they're real fancy picture frames, like gold leaf picture frames or something.
And you continued this bar just
I continued this bar because we still have some information we haven't taken into account, don't we? Or do we not?
I don't know that we need that bar.
No.
No.
Okay.
Oh, what's it? What numbers have we not put into the table yet?
She gave us some other information.
The totals.
She bought 15 frames. So if we total something, that total should be 15. Where should we total? We have columns? We have columns that could be totaled. We have rows that could be totaled. Which one would be the total that represented the 15 frames? How do we come up with the 15 frames total?
Would you add
Maybe my
X
idea
and
was
17, or would you add the number of large frames and the number of small frames?
Would you add the Y and the 5? What would you add? How would you get the total 15 frames? You're adding the number purchased, okay? That column total needs to be 15. Now let's think. They tell us how much she spends. She spends a total of $135.
Where do y'all think we're going to put the 135? It's a total for the...
It's the total of the prices. I agree. So, is it 135 or 105? What did it say? 135. So, here's something you're going to want to remember. If you're going to have a unique solution, you need the number of variables to equal the number of unique equations. The number of variables has to equal the number of equations if you're expecting a unique solution.
And
we have two variables.
Infinitely
you wouldn't want to
infinitely.
You shouldn't expect, there are infinitely many possibilities for this woman, how many frames she could have bought to satisfy this condition. If there's a solution, it's going to be a unique solution. So there are two variables. That means we need two equations. The first equation falls out from this column here. If you take the number of large frames plus the total number of small frames, that had better equal the number she bought, 15 frames. And now the next equation, the price equation. Each large frame costs $17. She bought X of those large frames. What's the total amount of money that she spent buying those large frames? It might be easier if I said just a number. Suppose that X was 2. That X is 2. How much did you spend on the large frames total? If the X were 2, she would have spent $34. To determine the amount spent on the large frames, you take the price per frame times the number of frames. 17 times X is 17X. That's all the money she spent buying the large frames. Well, let's add to it the amount of money she spent buying the small frames. How much money did this woman spend on small frames? You take the price per frame times Y. If that Y were 10, how much money did she spend? 5 times 10, 50. The price times quantity will give you the amount of money she spent on those small frames. So she spent $17X buying large frames. She spent $5Y buying small frames. If you add those two together, it better give you the amount she spent total, $135.
So you've come up with two equations with two variables, and how are you going to solve it?
Pardon me? You can use Cramer's rule, but
I like elimination.
I like elimination. I told y'all right off when we started this that elimination is my preferred method. So if it doesn't say use Cramer's rule or substitution, I'm going to use elimination.
But wait, am I pretty sure the answer's not going to be fractions?
If I thought there was a chance it was going to be a fractional answer, I'd go straight to Cramer's rule. But I think I'm pretty confident. Could she go in there and say, oh, I'm going to buy 4 2/3 of large frames? Maybe she could break one large frame into pieces. Could she do that?
Could you buy 17/11 frames?
Joseph, question. But yes.
Like on this problem here, on the test,
Mm-hmm.
will it say elimination or Cramer's, or could you use it?
It'll be up to you.
Okay.
It will be up to you. You'll still get the same answer, whether it's elimination, substitution, or Cramer's rule. I guess the reason I'm shying away from Cramer's rule is these constants are sort of big. Okay, let's go back. That was the first step we did. Remember, substitution, you need one variable solved, and then you substitute that stuff in to the other equation. And I said that's not really my favorite method. And if you're going to use substitution, you have to have one of the variables isolated in one of the equations. Here we didn't have one of the equations solved for X or Y, but we were able to get the first equation solved for Y very quickly. But with elimination, you have to have the same coefficient but opposite sign on one pair of like terms. There we had a 1 and a -1. You were able to add the two together, and 1x plus a -1x gives you 0x. You've eliminated the x's. Here, we were able to eliminate the y's because we had a +7 and a -7. This one, we didn't have like coefficients, did we? But we were able to we had opposite signs on the y, so we were able to multiply the second equation by 3, so that we have a +3y in the first and a -3y in the second. Let me... Okay, hopefully you all have been thinking about this problem. If you're going to use elimination, which variable should we try to eliminate? You could do either one, but I think one of them, the arithmetic, would be cleaner at least. Should we try to eliminate X or Y? Y? Well, we have a +5y here. Here we have a +1. What do we need it to be so when we add it to +5, the y's subtract out? Okay, so we're going to multiply. Where's my green pen? We're going to multiply the first equation by negative 5. So we're going to have there. Negative 5x minus 5y equals negative 5 times 15 is a negative 75. Then the 17x plus 5y equals 135 stays the same. Is this looking familiar to y'all? Do y'all remember doing this on Monday? When you add those two together, negative 5x plus 17x, that's a positive 12x. What's about to happen here? That's why we multiplied by that negative 5. We've gotten rid of the y's. Negative 75 plus 135, is that a positive 60? Dividing by 5.
No, by 12.
Dividing by 12. Dividing by 12, we get x equals 60 divided by 12 is 5.
No, we've already mentioned that you wouldn't expect fractions as answers. What about negative numbers? Would we expect negative numbers as answers?
Could this woman have gone over there to the store and bought negative 5 frames? Okay. So you wouldn't expect a fraction. You wouldn't expect a negative answer either. She's x. X is large frames. She went and bought 5 large frames.
I teach a business math class, and we do all this mortgage calculation. Calculate the price, the monthly payment for the house or the car. And this person's buying the $250,000 house, and what's the monthly payment? I get things like $50,432,000, or I'll get numbers like negative 3. Well, first of all, there's no mortgage payments that are negative, and the payment better never be more than the house. If your monthly payment is
more than the price of the house, then there's something wrong. But 5, I think, is a sensible answer. She bought 5 large frames. Okay, stop and think. We know she bought 15 frames total. How many small frames did she buy then? 10.
See, no algebra
15 minus
for
5
the
for the second answer. You can just think your way through it. So 10 small frames. This woman bought 5 large frames and 10 small frames.
You punch those in. You see,
she bought 5 large frames.
And then it's going to ask the small frames. 10. Okay. The nice thing is that all of these word problems set up just like this. Once you see one, practically, you still make the table.
You make a table and
then
stuff,
there better be 2 totals and stuff.
He's trying to say there'll be 2 variables, which means you need 2 equations. And by that, when I say, I really mean 2 unique equations. You can't just come up with the first equation, x plus y equals 15. I'm going to multiply 3 by 2. 2x plus 2y equals 30. That's not 2 unique equations. That's the same equation, just modified. If you're going to have a unique solution with 2 variables, you need 2 equations. Number 17, the cost to attend a movie is $11 for adults, with children, while children are admitted for $8. If a movie was attended by 63 people who paid a total of $552, how many adults and how many children attended the movie?
Well, I like the way this is set up. You see right off what the unknowns are. Adults, children.
Okay, switch over so they can see my paper. And
Attendance.
Now, let's see. How about, what are we looking for? We're looking for the number of adults that went to that movie and the number of children that went to that movie. I think I'll say the number of tickets sold.
I was going to say
Number of tickets. Or I guess the number attended. We don't know. X and Y. That's our unknown. Well, they gave us other information, so let's see. What else did they give us? Notice how we have to just keep going back and rereading the problem, making sure we've gotten all the information they gave us. They tell us the price for each ticket. Price per ticket. It's $11 for adults and $8 for children.
Y'all sort of see what I mean by they set up this sort of the same way. What are we going to do now?
Well, we're going to go back to the problem and reread. There's some information that we haven't taken into account. What have we not used yet? Okay, those totals. 63 people attended the movie, and they took in a total of $552. So switch back to my paper. 63 people attended. Where would that total go? Would it go at the end of the first row, second row, first column, or second column? The first column, the number of adult tickets plus the number of children tickets had better equal the total of 63 tickets. Now, they told us that the theater took in $552 from ticket sales. That's not that much, but they took in $14,000 from popcorn and drinks, so they're doing okay, I guess. But ticket sales, where do you think I'm going to put that $552? Here? What are we totaling for 552? Is it the number of adults? The number of children? Maybe the money, the cost, that price per ticket? We have two unknowns. We need two unique equations. Give me one of those equations. Oh, I've got to draw my total bar. Give me one of those equations. Okay, if you take the number of adult tickets plus the number of children tickets, you'd better get the total number of tickets sold, 63. What about the price per ticket? I see a total there. We need an equation there. How much money did they get when they sold X adult tickets? 11X. It's the price per ticket times the number of tickets. Price times quantity. 11X dollars is the amount of money they took in when they sold all of those adult tickets. How much money did they take in from selling the Y children tickets? 8Y. 11X plus 8Y gives us a total of $552.
Again, I wouldn't use Cramer's rule just because. Well, I guess I have my calculator.
Y'all want to see Cramer's rule? Y'all want to see it done with Cramer's rule? I'll do this one with Cramer's rule. You want to? Okay. First thing we do, we find the determinant D.
Should I open my calculator?
Yes. Open
you don't need it for the D, but I think you might need it for...
Okay. D, remember, it's the coefficients of... it's the determinant of the coefficient matrix. The coefficients of X are 1 and 11. The coefficients of Y are 1 and 8. So we multiply to give us an 8. What sign am I about to write? Minus. Multiply to give us 11. 8 minus 11 gives us a D value of negative 3.
Oh. dx and dy had better turn out to be what signs? Positive or negative?
Negative,
Better be
because
negative.
because you can't. If dx and dy are positive divided by negative 3, you're getting a negative number of tickets, which would not make sense. Now we'll find these green ink just isn't showing any good. Throw that green ink away. D sub x equals. Now, what am I going to write first? What am I going to write first for my x column? Okay, the constants. We're replacing the x column with 63 and 552. What am I going to write in the second column? That's the y values 1, 8. So here we go. We multiply. 63 times 8 is 504. What am I about to write? Okay, so minus, multiply, 552.
You don't need a calculator for that. It's time
to give us a negative. Is it a 48?
Okay, I'm feeling better because we know negative over negative will be positive. Okay.
You know something? You could just stop at this.
Oh, yeah.
You know x is equal to d sub x divided by d.
Oh, wow.
D sub x is negative 48 all over. D is a negative 3. Negative 48 minus 3 gives us...
No, divided by negative 3.
Negative 48 divided by negative 3 gives me a positive 16 adult tickets. So they sold 16 adult tickets. We could find dy and divide, but let's just stop and think. They sold a total of 63 tickets. 16 were adult. All the rest have to be children. So how many children tickets were sold? Okay. What's 63 minus 16? 47 children tickets. And it was 16 adult tickets. So 16 adult, 47 children.
We got to punch on both ends to check it. 16 adult and 47 children. Okay.
Any questions there?
Flip between the two pages to see if y'all sort of agree with my statement that they're set up very similarly. Right? No, maybe not. I thought they did. Okay.
Number 18.
Let's see. Oh, ignore this. Use Gaussian elimination. That's that stuff with the ones and zeros that we talked about.
Remember, we were setting up those augmented
matrices.
matrices. Well, so we just ignore that. We're using Cramer's rule, or elimination or substitution, I should say.
Oh wow!
And it's really up to you.
What a depressing problem. Mike works a total of
59 hours per
week.
week at his two jobs. He makes $8 per hour at job A and $9 per hour at job B. If his total pay for 1 week is $491 before taxes, then how many hours does he work at each job? What are our unknowns? What do we not know? It should be obvious. how many hours he works at his first job and how many hours he works at his second job. I always like it when the students say, oh, well, he should only work at job B because he makes more per hour. Last time I checked, I can't go tell my boss, hey, I want to work this many hours per week. They tell me, okay? So it's not really realistic to say, oh, he should just quit job A and only work job B. So, but I need to summarize this on a table. So I'll say job A and job B. And we've already said the thing we don't know is the how many hours worked. So I'll say number of hours. So he works X hours at job A and Y hours at job B.
Y'all fill in the rest of the table.
I'm going to make another column. Show them the problem. I'm going to make them tell me. What am I going to write as a column heading here? Or something. Give me an idea of what you think I should write. The pay, hourly pay. Okay. And at job A, Mike's making, what was it, $8 per hour. And at job B, $9 per hour. I think they gave us some totals. What were those totals?
What number are we going to put under the X and Y? I'm not going to say anything else. I'm just showing the problem. 59?
The 59. Mm-hmm. He worked X hours at job A and Y hours at job B. Adding the two together, we get 59 total hours. We know we made $491 before taxes. Where am I going to put that? Totaling all the money? What was it, 451?
No, wait, I think it was 491.
491.
You're taking out the taxes. Okay, so 491.
491. Okay. How many equations do we need? We need two equations because we have two variables. When I say equations, I mean unique equations. So, give me one of the two equations. Okay. X, you worked X hours at job A plus Y hours at job B. That had better give us a total of 59 hours. 59 hours.
Oh, and that's a penmanship
That's
award-winning
Y.
Tim.
It is. Penmanship award winners always have flair, okay? So you were the Tanya Harding of writing, Tony. No artistic flair. You can do that triple axel, but there was no artistic flair.
They don't know what you're
to
talking
it.
about,
So,
Tim. This was before they were born, so
okay.
what you're talking about.
Okay. Oh, now the hourly pay, give me an equation involving dollars. 8x, so he makes $8 per hour times X hours. That means that Mike is making $8X at job A. 8X is all the money he made that week at job A. How much money did he make at job B? 9Y. Price per hour. The pay per hour times the number of hours. And when you combine, here's all the money he made at job A. Here's all the money he made at job B. Putting those two together, he gets a total of $491. What do y'all think? I liked Cramer's rule the first time. What do y'all think? Should we use Cramer's rule again? Yes? Okay. So, you think I'll remember next semester? Oh, we liked Cramer's rule, Tony.
I don't think so. I think I'll be like, I don't like Cramer's rule. But
I'm going to go to my calendar and put on February, what's the day? On April the 15th, I'm going to write for my calendar next year. Use Cramer's rule for word problems.
Okay.
Okay. So what numbers am I going to write first here for D? 1 and 8.
Uh-huh.
And then 1 and 9. we multiply 1 times 9 is 9.
Oh, wow.
Minus, oh, this is nice, multiply. So what are we getting for D? 1. So whatever we get for D sub x, that's the value of x.
Oh,
And that's about the nicest D value possible. Suppose we'd gotten, we haven't mentioned this, suppose we'd gotten a D value of 0. Do systems always have unique solutions? Could we divide by 0? Look back over here. Suppose we'd gotten a D value of 0. Can we divide by 0? That means it's one of the two special cases, either no solution or infinitely many solutions. If you went on and found D sub x and you got another 0, 0 over 0, infinitely many solutions. If you had gotten a D sub x other than 0, like a negative 48 divided by 0, that's the parallel line situation. So Cramer's rule will even spot those special cases for you that we discussed the last time. Fortunately, though, we didn't get a D value of 0. Now let's find D sub x. D sub x. What am I going to write in the first column? Okay, those constants, 59 and 491. What am I going to write in the second column? It stays that value of 19. And here we go. Multiply 59 times 9, that's like 59 times 10, which is 590 minus 59, which gives me A. I'm not going to look at Tony's. Is it 531? Okay. Minus.
Do I need to punch that in the calculator for you, Tim?
To give me 531 minus 491 gives me a nice positive 40. And Cramer says x is equal to D sub x divided by D, 40 divided by 1. Mike worked 40 hours at job A. How many hours did he work at job B? We know he worked a total of 59 hours. 59 minus 40. You don't have to write that down. I'm just showing you my logic. 19 hours at job B.
40 and 19.
So he worked 40 hours at job
full
A.
time at job A.
So he had a full-time job and he worked 19 hours extra at job B. Any questions there? Now I want to go back to number 15. I just think this wording is clunky, okay, on number 15. That's why I always wait to look at it until the end.
Notice that same pattern.
A basketball player scored 20 times during one game. He scored a total of 33 points. 2 for each 2-point shot and 1 for each free throw. So he got 2 points for a 2-point shot and he got 1 point for a free throw. So maybe they should change the name of 2-point shots to paid shots. A free shot, you get 1 point. A paid shot, you get 2 points. It's that two points for each 2-point shot that I don't like. It's just that wording. It sounds redundant. Like I'm saying too many times. But anyway, number 15.
What are we trying to find?
They're asking right there, how many 2-point shots did this player make? How many free throws did this player make?
What are we going to identify as our unknowns?
Maybe the number of 2-point shots. And the number of free throws. From my limited memory of basketball, playing basketball, I remember in school, of course, I remember that the free throws are from the line, and so they're easier to make. You're just standing there throwing, so that's why you only get 1 point for the free
Tim,
throws.
you don't have to discuss why that is.
But we say the thing we don't know.
Let's say about
the
right here.
What am I going to write? X, Y,
Yeah.
and I'm going to identify those as it's the number of shots. How about, I'm feeling lazy, I'm just going to say quantity. Is that okay?
How many?
That's not, I should have written number of shots. Well, it's too late now.
Now here we didn't get a dollar amount like the other ones.
But we did get a point value.
Mm-hmm.
A point value.
What numbers is it going to write? Here and here.
Each 2-point shot is worth how many points? 2. There's that redundancy that I don't like. Each free throw is worth only 1 point. Let's go back to the problem again. They gave us some totals, didn't they? Ah, there it is. The totals were given at the beginning, weren't they? This basketball player scored 20 times during one game. So, and he scored a total of 33 points. Where am I going to put the 20 on this table?
Wait, 20. Oh, it is 20.
He scored 20 times. Okay, under X and Y, he made X 2-point shots. He made Y free throws. If you add that together, that better give you the total times he scored. And what about that 33? What are we totaling there? The point values, you got 33 points.
Having set it up like that, are the equations going to fall out like the other ones? What are the two equations?
Okay. He made X 2-point shots plus Y free throws. So total, that better give us the 20 times he scored. What about the point value equation? Okay, 2x, that's the number of points per shot times the number of shots, plus, how many points did he get from the free throw? 1 times y, which is just y, equals a total of 33. Any questions on our logic setting up those equations? Okay. Substitution, elimination, or Cramers? What do y'all want to use? Cramer's rule? Okay, let's use Cramer's rule. And once we find d and d sub x, we'll probably be able to tell the y value. Surely we'll be able to just subtract to determine the y value.
Hey,
what
and we
numbers?
have fractional answers or negative answers here?
No, okay. First column, what do I write? 1 and 2, the coefficients for x. Second column, oh, that's nice, 1 and 1. So we multiply 1 minus multiply 2, 1 minus 2, we have a d value of negative 1. That means that d sub x, when we find d sub x, it had better be negative as well. So now we'll find d sub x. What will I write first? I'm replacing the x column with those constants, 20 and 33. The second column stays 1 and 1. So we have multiply 20 minus, multiply 33 to give me a negative 13. So according to Cramer, x is equal to d sub x divided by d. Negative 13 divided by negative 1 gives us a positive 13. Now where is x? Right here, this player made 13 two-point shots. Well, how many free throws did he make? Remember, he made a total of 20. He scored 20 times. 7. So here's my logic. I wouldn't expect you to write that out. But 20 minus 13 says that there were 7 free throws and 13 two-point shots.
13 two-point shots and 7 free throws. Checking that. Okay.
Any questions there? Okay. Any questions you want recorded? Okay, let's do this.
Okay.